Hello everybody. So now we are trying to put everything together. We understand the effect of temperature, the effect of pressure, and now on the phases. And now we want to see the combined effect of pressure and temperature. And to do this, we have a diagram that's called PT diagram. So it's pressure temperature diagram. It's called this because we have pressure on y-axis, temperature on x-axis. So based on what we discussed the last two videos, we can now have an expectation where the liquid phase will be and where the vapor phase will be. So we can tell that liquids or the material would be in the liquid phase at low temperature and at high pressure. And the other way, we saw that if you increase the temperature and if you decrease the pressure, boiling will happen. So we have an expectation that the phase of high pressure, low temperature, which is this region, is going to be a liquid phase region, and the region of low pressure, high temperature would be a vapor phase region. And we know the transition will happen at a combination of pressure and temperature. So for the liquid at normal pressure, the evaporation will happen at the normal boiling point, which is the boiling temperature. So this is the point where evaporation will happen. Let's say for water, this is 1 atmosphere and 100 degrees Celsius. We have another example that we covered, which is the pressure cooker, and we said that this is in the case of pressure cooker, the pressure is high and the temperature is high as well for boiling. The boiling of water would be at higher temperature. For the case of the vacuum, which is the video that we saw in the beginning of the discussion of this part of the chapter, we said that the vacuum would be the vacuum was low pressure and the boiling happened at low temperature. So we have three dots or 3 points that indicate different combinations of pressure and temperature, and these combinations are the combinations at which evaporation takes place. And this is the PT diagram that we can draw. So the PT diagram is a diagram that we see and for this diagram we have a line which is the locus of the evaporation conditions for combination pressure and temperature, and it splits the region into two or the area into two regions, a liquid phase and a vapor phase, and this line is the transitional line between the liquid and vapor phase. So this is a very important thing. So this is for the liquid phase. This is the vapor pressure line. This is what we see now. We will see that this is not going to be only the vapor pressure, but this is for what we see now is just the vapor pressure. So this line is called the liquid vapor saturation curve, and that's why the vapor pressure sometimes is called the saturation pressure. We mean saturation because if you remember the 2 videos ago, we said that the liquid that is about to evaporate is called saturated liquid, and the vapor that's about to condense is called the saturated vapor. So this is the saturation curve because it's where the liquid is saturated and where the vapor is saturated. So this is what we have now as a crude idea of the PT diagram. If we look at the normal data, this is what we would see for the PT diagram for liquid water. We have here the liquid phase, we have here the vapor phase, and we see that still at different pressures with different temperatures. Of course, the range here is very, very large for pressure. We have from 0 to 250 atmospheres, so it's a very, very wide range of pressure, and that's why the temperature range is high as well. We can see boiling here will happen at 375 or 380 degrees Celsius. So to boil at this very, very high pressure, we need to have very, very high temperature. This is an important thing. One thing that we would be interested in here, which is not something that we are discussing regarding the evaporation or not, but it's regarding the way we are displaying the numbers. One thing that would be very deceptive here is the points that are at low pressures. So the scale here is very large. It's 200 from 0 to 250. So in order to cover this whole range, we had to squeeze the increment. So for each increment here, we go from 0 to 50, from 50 to 100, and even these minor grid lines are 10. So it's 0, 10, 20, 30, 40. So the smallest unit that we have here is 10 atmospheres, which is a lot. If you're interested in low pressures, then what you would see here is that the points from 0 to 170 degrees almost are all squeezed in a very small region that you cannot distinguish between them. And actually, if I am looking at them, I would think that this point and this point have the same pressure, which is not true. So this is one problem that we face when we have scales that are or data that are on a scale or a very wide scale. We would expand the scale a lot, so that this will lead to the diminishing of the values of the points at small values of the parameter, which is the pressure. So we are losing some data here, or we're losing the meaning of some data. And in order to solve this problem, we use another scale, which is called the logarithmic scale. So this logarithmic scale is a scale, instead of going with a linear scale like this, with a constant increment from 0 to 50, 50 to 100, so we have increment of 50, we now are using an increment of powers. So we have 10 power minus 2, 10 power minus 1, 10 power 0, which is 1, then 10 power 1, 10 power 2, 10 power 3. So this is the increment that we are dealing with. We are dealing with powers, not or the increase in power, not the increase in the actual value. And in this case, you can see now the values are very clear. So you can now see the difference between this point and this point. So this is the boiling temperature or the saturation temperature at pressure of 0.1 atmosphere. It's around 45 degrees Celsius. Under pressure of 1 atmosphere, it's 100 degrees Celsius, and at 2 atmosphere, it is 120 or something. So this is very clear now that we can see the numbers. We can see that this is 100. So this is the point at 100 degrees Celsius. This is increasing, and so on. You would also notice here that the minor grid lines are not uniform. So you have here this is 1. So this is going to be a large difference, or a big difference between this one and the next grid line, and then it gets smaller until we reach the 10, and then it's big and then gets smaller. So it's repetitive scale, and this is because it's a log scale. Here you would see here that the scales here, or the minor grid lines, we have here 10 power minus 1, which is 0.1. This is going to be 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, then 1, then 2, 3, 4, 5, 6 until 10, then 20, 30, 40 until 100, then 200, 300, 400 until 1000, and so on. So if we look at, just to clarify this point, let's say we want to find out what is the value of the pressure here. So the pressure here, to find this pressure, we will look at what is the major grid line before it, which is 10. So this is 20, 30, 40, 50. So this is 60. This is the pressure of 60 atmospheres, and so on. So now this is a better way of representing the numbers, because this is a very convenient thing that we can use, and it's a very common case. In many cases, you will have scales that are very big, so you need to make sure that you don't lose the meaning or the value of some numbers because of expanding the linear scale. So we shift to the logarithmic scale. This scale that has log on y-axis and linear scale on x-axis is called the semi-log plot. So this is semi-log because its part is log and part is linear. If it's log on both scales, it would be called log-log scale. So these are common terms that we use in engineering applications. Anyway, so let's go back to the point that we were making, that this is the saturation curve, this is the pressure, this is the temperature, and we applied this on the liquid vapor phases. So now we want to expand this to the three phases, and this is what we call the three-phase PT diagram. The part that we or the diagram that we're looking at is a diagram that is splitting the region or the combinations of pressure and temperature into three regions. One region here, one region here, and one region here. And of course you would be expecting that these are the three phases. One of them is solid, one is liquid, and one is gas. So again, we know that the gases would be at very high temperature and very low pressure. Liquids would be it would be the intermediate case, and then the solid would be at very low temperature. You think of ice, low temperature, and different pressures. So this is what we see here. This is the region of solid. Think of ice. It needs very low temperature, so the low temperature region would be the solid region. And then we will have the liquid, which we call the subcooled liquid, which is not saturated liquid. This is the liquid phase, and then we have the vapor phase in this region, which for liquid water or for water is going to be superheated steam. Superheated, which is higher than the saturated vapor temperature. So this is the diagram. This is how it's split. We have now three lines. We called this line before the liquid vapor saturation curve. Now we have the liquid solid saturation curve. This is the line that splits between or the regions of or areas of liquid and solid. So this is where melting takes place and freezing takes place. So if you go this way, it's melting. If you go this way, it's freezing. And we have the solid vapor saturation curve. And this might be very weird for some of you, because according to the same concept, here we go from solid to liquid and from liquid to solid, which is very logical. We see this a lot. But here we will go from solid to gas and gas to solid, or solid to vapor and from vapor to solid, which is a very strange thing. This phenomenon is called sublimation, that the liquid, the solid turns into gas directly without going through the liquid phase. But this happens, and we will see a video for this shortly. So now let's take this line here. So this line that we have here, it's at constant pressure line. So this constant pressure line, if we have solid, we will heat it, then we will reach a point where we have the melting, and then if we keep heating, then we will have boiling. So this temperature is called the melting point. This is called the boiling point. Okay. This point here, which is at the end of the liquid vapor saturation curve, is called the critical point. The critical point is a point after which the material behaves after the critical temperature and critical pressure. This is called the critical temperature, and the pressure at this point is called the critical pressure. After this point, the material behaves in a different way, so that's why it's called material at the critical condition. So this is the critical point. We have also here, this is a very interesting point, which is the intersection of the three lines. We call it the triple point. The triple point means that the three phases are coexisting and are in equilibrium at the same time. We will see this now. So let's try first look at the phenomena of sublimation, which is turning the solid into gas. So this video is a very nice video. We have here, this is called solid ice. It's not solid ice, it's called dry ice. I'm sorry, it's called dry ice. Dry ice is solid carbon dioxide. Okay, so this is carbon dioxide that's frozen, so it's in a solid phase. And here we have a small beaker or flask that's filled with water at normal temperature, 25 degrees, 30 degrees. And what will happen here is we will see that what happens when we put some of this dry ice in water. So what you're seeing here now is the sublimation. Carbon dioxide is turning into vapor, so it's not melting, it's in the region below the triple point, so it's now turning from solid directly into vapor. So this is the sublimation. You would see this is very, very clear here. It's the solid is bubbling, so it's not it's not melting, it's sublimating. So this is the first thing that we would see, or the first example, or the first phenomena that we can understand now. So if we go back here, you would see this is what happening. The carbon dioxide is turning from the solid under the triple point from here to here directly. Now let's look at the triple point, which is a very the triple point is a very interesting phenomena. So what we would see here in this video is water at the triple point. Triple point of water is at 0.00611 bars and 0.01 degrees Celsius. So it's very accurate point of pressure and temperature. It's well studied. So at the triple point, what we will see here is this is a container that is or water that is kept in vacuum chamber under very low temperature, which is this temperature, and the pressure is decreasing until it reaches the critical at the triple point pressure. So what you see now is water is at the triple point. There is ice, so it's solid. We have liquid inside and bubbles that are formed. So you have evaporation, you have condensation, you have sublimation, you have the freezing and melting, all are happening at the same time. So a triple point is a very interesting point. It's a very special point. It happens at very special conditions of pressure and temperature. And this is what you see. The liquid, solid, and vapor are coexisting at the same time. The phenomena of evaporation and having a solid, liquid, and phase are all happening together. So this is what we mean by a triple point. So they coexist, and this is what we mean by the triple point. Next time, inshallah, we will start looking at the tables. We have some properties that we can find in tables. Right now, we are just interested in the properties of steam, which are the enthalpy. So next time, and I hope this part or the 3 videos that we did this and the previous 2 videos will give a good idea about the phenomena that we need to or the basics that we need to understand about the transition from a phase to another, and the saturated vapor, saturated liquid. And I hope these terms are now clear. So, and this is why I'm putting a lot of time in this, to make sure that these concepts are very clear, the terms are well understood, because this is what we will be depending on when we look at the tables that we will look at in this appendix next time, inshallah. So I'll see you then. Goodbye.